If you have trouble, please let me know. I've gotten a few email questions. You can use, I think, the Ask My Professor utility on WebAssign. Let me know if that's not working. There are about a third of people haven't submitted anything for those 2 assignments. So please make sure you get those done. They shouldn't be that hard. If you're running into trouble, I'll try to help you. I can set up extra office hours this afternoon. I'll be available, say, from 4 to 5. If you've got more questions that are nagging at you. So please don't let these assignments go undone. And the next 2, assignments 3 and 4, cover the matrix identity, matrix algebra, and what is it? Linear combinations, applications of that idea, connections of the idea of linear combination to matrix products. So again, by the end of today, you should have everything you need to make good progress on all of those assignments that have been posted so far. So don't leave them till the last minute. All right, so we're going to continue our development here. As usual, if you have questions, please ask. You can ask in the chat if you want. If I don't see your chat request, please just unmute yourself and ask the question. Get my attention. All right, so we've got those first 2 WebAssign assignments due tonight. Get them done. Let's see here. And I want to talk about the matrix inverse for a little bit. And before we do that, I need to talk about the identity matrix. So if we have a scalar equation, ax equals x, then of course you know a is equal to 1. If you've got a matrix version of this type of thing, ax is equal to x, and let's say a is n by n, x is n by 1, right? Notice that this is going to work when A is a square matrix. Okay. This is sort of acting like the number 1 when we're dealing with scalars. I multiply the matrix by a vector, I get the same vector out. And the same thing, might happen with a matrix-matrix product, right? You might have a matrix A times the matrix B gives you the matrix B. A is acting like the number 1. Well, the matrix that's going to do this for you has a few special properties, right? You can see from an equation like this that this is going to work, right? This is going to be possible if and only if the matrix A is a square matrix. It has to be n by n, same number of rows and columns. And in fact, matrices that act this way are called the identity matrices. Okay. So there's a chat that I missed here. What was the question, or did you just need more time?
I just needed more time. Thank you.
Okay.
I'm good.
No worries. Are you ready, Catherine, to go on?
Yes.
Okay. So the matrices that act this way are called the identity matrices. We give them the symbol capital I. Sometimes we do a sub n. The subscript n means the n by n identity matrix. And if it's clear from the context, the size of the identity matrix, often we won't bother including that subscript. If I'm talking about I sub 1, well, that's just effectively just the number 1. I sub 2 would look like this. I sub 3 look like this. And in general, I sub n has entries of 1 on the so-called main diagonal, right? These are the entries where the row index equals the column index. Right, so for the 3 by 3, I've got a 1 here in the first row, first column, a 1 in the second row, second column, and a 1 in the third row, third column, and zeros elsewhere. Everywhere else. Okay, so let's just verify that this does the job we want it to. Just by a simple example. Here's a 2 by 2 identity matrix. I'm going to multiply it by some arbitrary 2 by 2 matrix. And what am I going to get out? So this is 2 by 2, 2 by 2. Inner indices match, so we know we can do that product. The outer indices are 2, 2, so we know we get a 2 by 2 matrix as our product. For the 1, 1 entry, we go across. Sorry. Excuse me for a second. Hello? Sorry, that was a call from a doctor. So let's see, we were doing the first row, first column, right? We go across the first row of the left matrix, down the first column of the right matrix, and we get A out. First row, second column in our product, go across the first row of the matrix on the left here, down the second column, we pick out the B entry. And then down here, we use the second row, first column, we get the C entry. Over here, darn it. Over here, we use first row, second column, we get our D entry. All right, so that does the job. And what happens if we actually go on the other side? Okay, so again, we go across the row on the left, down the columns on the right, we pick out an A, we pick out a B, we pick out a C, pick out a D. Right, so we've shown that I times A is equal to A here. A times I, again, is equal to A. All right, so that's just one example of how the identity matrix works for a 2x2 matrix in the 2x2 context. Why do we care about this? Well, let me just pause, ask everyone, get down what you need from this page before we move on. Let me know when you're ready to move on, please. Okay, are we ready? Okay. So imagine we're trying to solve a system. AX is equal to B. Okay, and let's say A is a square matrix. Well, the process of solving this, right, by reducing to RREF form, essentially what we're doing is we're turning our coefficient matrix into the identity matrix. Okay. And we can think of what we're doing by going back to the scalar example, AX is equal to B. Well, we want to solve for X. We could do that by multiplying on each side by 1 over A. A over A is equal to 1, so X is equal to B over A. Well, that's fine in the scalar case. However, there's no notion of dividing by a matrix. We can't do 1 over A on each side here. So the problem here is that division by a matrix is not a defined operation. Right, so how did we get rid of that coefficient, right? We can't just divide by this matrix coefficient, but we somehow, identity matrix times X is just X, and that's going to be our solution. How did we get to the identity matrix here? Well, essentially what we did with these RREF operations, the allowed elementary row operations, each of those you could characterize as a matrix that gets multiplied by your given coefficient matrix, and you get a new coefficient matrix. So with all of those operations strung one after the other, that's a product of matrices. That's essentially a matrix that you've multiplied to go from your original coefficient matrix A to your identity matrix here, I. So does everyone have what they need from this page? Are we ready to go on? Are we good? Okay. So the idea is we've got our matrix A. We want to multiply by something to get the identity matrix. And if we think back to what we did in the scalar case, 1 over a, we sometimes think of this as a to the exponent minus 1. That minus 1 exponent sort of plays double duty in math. Sometimes we think of an exponent of minus 1 meaning 1 over the quantity. Sometimes we think of that exponent minus 1 as representing the inverse. And in fact, the multiplicative inverse, right, of a number is just 1 over the number. So the two things mean exactly the same thing in the scalar context. That's not always true. Here, what we're going to do is we're going to introduce what's called the inverse of a matrix, which is another matrix. And if A is n by n, then A inverse has to be n by n as well. The inverse is only defined for square matrices because we want it to be the case that A inverse times A is the same as A times A inverse. And both of these need to be the identity. Right, so notice that for the dimensions to work out for both of these products to exist, the matrix A has to be square and the matrix A inverse has to be square, and they have to have the same dimensions. All right, and the matrix I that comes out here is going to have the same dimensions as our matrices A and A inverse. Okay, and if you think about what our motivation was here, that actually gives you a way of thinking about computing the inverse for a matrix. So the connection right, so the idea is that we can start off with an augmented matrix where we put our whatever matrix we're trying to invert on the left-hand side, put the corresponding identity matrix on the right-hand side, do elementary row operations. Essentially, we want to get the matrix A to its RREF form. That's got to be the identity matrix if it's invertible. And at the end of the day, when we've done that, we're going to replace our identity matrix on the right-hand side by our inverse matrix. Okay. So that gives you basically a strategy for solving your problem, for finding your matrix inverse. So let's actually try to do this. Let's do an example. If our matrix A is 3, 7, -1, 4, matrix A inverse is what we want to find. We're going to build an augmented matrix with our given matrix on the left. It's a 2 by 2 given matrix, so we want the 2 by 2 identity on the right-hand side. And now we're going to do elementary row operations. We're going to try to get the identity matrix here on the left. Okay, so there are, of course, there's not just one way to do this. You can do this in lots of ways. So let's say that we start by taking that first row and dividing by 3. Okay, so I multiplied every entry in the first row by 1/3 so that I could get my pivot entry of 1 all the way to the left on the top row. Okay, everyone good so far? And next, what's our next step? Was there a question? So what do we do once we have a pivot? What do we want to happen in the rest of that pivot column? Okay, so somebody's telling me the operation to do. We want to make zeros everywhere else in that column. So we could do that by adding row 1 to row 2. So we have row 1 stays the way it is. We're going to replace row 2 by row 2 plus row 1. So 1 minus 1 is 0. 4 plus 7/3. 1/3 plus 0 is just 1/3. 0 plus 1 is 1. And 4 is the same as 12 over 3. 12 plus 7 is 19. So hopefully I did my arithmetic correctly there. Does everyone agree with that step? Everybody good? All right, so next step, we've got this leading entry in the second row. We want to make that into a 1. Right, so we can multiply through by 3 over 19. So 3 over 19 times 1/3, we're going to wind up with 1/19, I think. 3 over 19. Okay, does that make sense, everyone? Very good. And now we're going to work on this entry. We want to get that to be a 0. So we can take row 1 and replace it by row 1 minus 7/3 times row 2. So we're going to have row 1 is 1/3 minus 7/3 times 1 over 19. And then row 1 minus 7/3. So that's going to be minus 7 over 19. So I have to do a bit of arithmetic here. So let me just go up to the top here. 1/3 minus 7/3 times 1/19. So there's 3 times 19 is my common denominator. Think of that 1/3 multiplied by 19 over 19. So we'll have 19 minus 7 on the top, or 12 on the top. I could cancel common factors of 3 on top and bottom. I'm going to be left with 4 over 19 there. All right, so this should be the inverse of our original matrix.
Can you explain? Yeah, can you explain what you did for the 1/7/3 0 1? How you made it 1 0 0 1? The last operation you did.
The last step here.
Yeah, the last step.
So what did I do? I want to make that 7/3 entry go to a 0, right?
Mm-hmm.
So I replaced row 1 by row 1 minus 7/3 times row 2. Right, so 7/3 times 1 is 7/3. I subtract that from 7/3, I get 0.
Okay.
Okay, so think about multiplying that whole second row by 7/3 and subtracting it from the first row. Okay, so hopefully I did my arithmetic correctly. So let's check. We've got our matrix A. It's got entries 3, 7, -1, 4. And then we're saying that the inverse is 4/19 minus 7/19. And then on the bottom, 1/19, 3/19. All right, so let's check. We multiply through, we get 3 times 4/19 plus 7 times 1/19 in the 1, 1 entry. And then the 1, 2 entry, we've got 3 times minus 7/19 plus 7 times 3/19. And then the 2, 1 entry, we've got -1 times 4/19 plus 4 times 1/19. And then the 2, 2 entry, we've got minus 7/19 plus 4 times 3/19. And if you simplify here, notice the 1, 1 entry, we've got 12 plus 7/19 or 19/19, that's 1. These two entries cancel out to 0. Pretty easy to see. And the 2, 2 entry again is 19/19, simplifies to 1. So we really did what we were supposed to. We found the inverse of the matrix. Now, this
Can you just
strategy,
explain how you got those ones again?
I'm just simplifying this arithmetic expression. So 3 times 4/19 plus 7 times 1/19. That's 12/19 plus 7/19, or 19/19, which is 1.
Okay, thank you.
Okay. So is it clear where that 3 times 4/19 plus 7 times 1/19 is coming from? Right, we go across the row, down the column, use the first row, first column for the 1, 1 entry, and so forth. Is that clear? Yes, okay. All right, so that's basically how things work. For a bigger matrix, of course, the amount of arithmetic you have to do increases in general. This is not the most efficient strategy for computing the inverse of a matrix, but it's fine as long as your system is not too large. So 2 by 2, 3 by 3, even a 4 by 4, you could do this by hand without much of a problem. It gets to be a little tedious when the matrix is too big. And there are more efficient ways of actually doing this numerically, but this lets you see exactly what's going on and lets you use what you know about elementary row operations and the RREF. Okay, so there really is a connection there. Now, there is a formula for the inverse of a 2x2 matrix. And in fact, there are formulas that you could write down in principle for the inverse of the matrix. These get very complicated very fast. Typically, only the formula for the 2x2 matrix is ever something that you would bother to try to memorize. Okay, so just a little bit of terminology. If the inverse of the matrix exists, then we say A is invertible. And A is non-singular, right? These mean the same thing. Right? Invertible or non-singular just means that the matrix has an inverse. If A inverse does not exist, then we say that A is non-invertible, or A is singular. Again, these are just two words that mean the same thing, two different ways of saying the same thing. The inverse doesn't exist. And it's clear that there are matrices that are not invertible, right? So 0, 1, 0, 0 is an example of a singular matrix, a matrix that doesn't have an inverse, right? So let's see what would happen if we actually tried to compute the inverse of this guy. So before we go on, has everyone got what they need from this page? Good. Okay. So let's use our strategy. Well, we're immediately in trouble, right? We're trying to get towards 1, 0, 0, 1. We have no way of creating a 1 in any of these leftmost entries. So that is telling us that this matrix is not invertible. It does not have an inverse. Okay. Now, is this argument clear to everyone? Making sense? All right, so let's go back now and think about the linear system, right? This is sort of what's motivating everything we're doing. If the inverse of that coefficient matrix exists, then we can left multiply by it. We remember matrix multiplication is associative, so we can group the A inverse times A. We know that's the identity matrix. We know identity matrix times anything just gives you the anything. So we have a formula for the solution. Okay, it's in terms of the inverse of the coefficient matrix. And notice that there's no free parameters. The solution is unique. Okay, so we talked a little bit previously about the structure of the solution. We saw that when you do reduce your system to RREF form, you might have a unique solution. You might have free variables and have a non-unique solution. Well, here's a way of telling whether your system is going to have a unique solution. If you look at that coefficient matrix and it's invertible, you know immediately that the solution has to exist and it has to be unique. Okay, so there's a number of statements that we could think about here. Let's say the matrix has a pivot in every row. Does that mean that the matrix has to be invertible? So I'm asking you all, what do you think? No. False, false, false. Okay, so in fact, the answer is false. Just because you have a pivot in every row, that doesn't even mean that the matrix A is square. So certainly that's false. Right, so for example, here's an example of a matrix that has a pivot in every row. It's not even a square matrix, so certainly it's not invertible. Here's another true-false statement. If AX is equal to B, keep forgetting to write if, AX is equal to B has a unique solution, then the matrix A is invertible. What do you think, true or false? So I see some trues. So this is true sort of conditionally. True if A is square. You have to be a little bit careful here because if you have more equations than unknowns, but those extra equations essentially don't give you new information, that's going to lead you to rows of zeros at the bottom when you get to the RREF form. And that's not going to mess up the fact that your matrix is essentially you're going to get a unique solution, even though your matrix as given is not square. But in this case, essentially, you could look at a subsystem which has all the information and has a square matrix. So this is a little bit delicate. So let's say your matrices A and B are square matrices. So the set of matrices that are n by n, let's say they have real entries. And these are invertible. Then AB inverse is equal to A inverse B inverse. So true or false? Well, you put these together, it's not immediately clear how to operate here. And remember that it's not allowed to change the order here in general. So in fact, in general, this is going to be false. AB inverse is going to have to be B inverse A inverse. And you can actually see that by putting these together, multiplying these together. Come on. Right, so if you regroup, the B times B inverse gives you the identity. That identity you could group with either the A or the A inverse. And now you can see what the identity is. So in fact, the inverse of a product of matrices is the product of the inverses of the matrices in the opposite order. Okay, so we want to go back to the last slide. Okay, did you just need to copy something, Megan? Or did you have a question? Okay. So in general, the inverse of, if you've got a string of matrices multiplied together and that's invertible, that's going to require that every single matrix in that product is invertible. And the inverse of the product is going to be the product of the inverses of the factor matrices, but in the opposite order. And you can see why that works by this calculation. Okay, so is that argument clear to everyone? Is that good? Thanks. Okay, so let's say that A is a square matrix. Whose RREF has a 0 row. Okay. Is A invertible? So this is now a yes, no question. What do you think? So remember our strategy. We have to get to the identity matrix on the left. Does the identity matrix have any rows of all zeros? It doesn't, in fact. So if when we turn our A into its RREF, if we have a 0 row, that means the matrix is not invertible. Okay. And as a follow-up to that, if the RREF of A has no 0 rows, is it invertible? So here, you need to, oh, sorry, question C was false. So yeah, C was false. So it turns out that the inverse that you were told to look at was just the string of the inverses of the factors in the same order, but you have to reverse the order of the factors. Okay. All right, so RREF of our matrix A now has no 0 rows. Does it have to be invertible? So let me give you an example of a matrix in RREF form. Okay, so notice that RREF doesn't require the matrix to be square. So in fact, you can give sort of a conditional answer here. If your matrix A is square and it has no 0 rows, then in fact it is invertible. But in general, you can't say just because there are no 0 rows, it has to be invertible. All right, so you have to think about the geometry of what's going on a little bit. So is that argument clear to everyone? Are there any questions at this point? Okay, makes sense, good. All right, so we're gonna move on here. And we're gonna use what we've been developing to say something about the structure of solutions. Okay, so here's a definition. A homogeneous linear system has the form AX equals 0. So it's homogeneous because this right-hand side is 0. Okay. Now, there's always a solution to a homogeneous system. right? Matrix times the zero vector is going to be the zero vector. So 0 always works as a solution. So that's important to note. This is sort of a lemma is sort of an intermediate result that's important. So the linear combination of solutions to a homogeneous linear system is also a solution. Right, so if AX is equal to 0, x1 say, and AX2 is equal to 0, then A times C1 x1 plus C2 x2 is also equal to 0. And you can see that by distributing this product. You can move the constants to the front and then remember that A times x1 and A times x2 both vanish because x1 and x2 are solutions to the system. Okay, so if I have a homogeneous linear system and I have some solutions of that system, I can build more solutions by taking linear combinations of the solutions that I know. Okay. Does that make sense to everyone? Good, excellent. Does everyone have what they need from this page? So a lemma is just a little theorem. Okay. Just a result. Any more questions? Okay. So here's another definition. We say that x sub h is the general homogeneous solution to AX is equal to 0 if any solution oops. Okay, so the idea here is that you've got your linear system, it's homogeneous, and let's say that you find some solutions, x1, x2, x3 all the way up to x sub k, you know that by our previous result that any linear combination of those is also a solution. So I can take some constant multiple of my first x1 solution there, another constant C2 times my second solution x2, and so forth. And if any solution to that system can be written in this form, then we call that the general homogeneous solution. And it's important to note this is not unique. Okay, so let me just give you an example to make it clear what we're talking about. So actually, before I go on, does everyone have what they need from this page? Everyone good? Okay. So say that your system AX is equal to 0 has 1, 0, and 0, 1 as solutions. Then for any C1 and C2, C1 times 1, 0 plus C2 times 0, 1 is a solution of the system. Okay. So that lets you write all the solutions in a certain form, but notice that you could represent your general solution actually in terms of these two other vectors. Okay. So these are also solutions, right? The first one, I take 1, 0, I subtract 0, 1. The second one of these, I just add my two vectors there. I could represent a general homogeneous solution as a linear combo of these two vectors. Right, so having the general solution is useful, but it's not something that you can specify uniquely. If I can write my solution like this, I could write it as a linear combination of the second pair of vectors just as well. Okay, and that's something that you see in general. All right, so is the idea on this page clear to everyone? Are there any questions? Everyone good? Okay, so we're going to move on. So particular solutions. So we talked about homogeneous solutions. We also have particular solutions. So we can look at the system AX is equal to B. So remember when that forcing vector on the right-hand side was 0, we say the system is homogeneous. When that vector B is not 0, we say the system is non-homogeneous. Okay. And the solution of the system takes the form. Come on, why is this going? X is equal to X subhomogeneous, the general solution of the associated homogeneous problem plus X sub P. Right, so if I replace the B by 0, that's the associated homogeneous problem. XH is some general solution of that associated homogeneous problem. X sub P is a particular solution of the non-homogeneous problem. Okay, and of course it has to depend on that forcing vector, the B. So particular means that it's some singular, some individual solution. Okay, it works as a solution of that full non-homogeneous problem. So let's see how this works. So say we want to look at the system AX equals B. And we know that X sub P satisfies A times XP is equal to B. So XP is a particular solution of this non-homogeneous problem. Well, try looking for the solution of this non-homogeneous problem as X is equal to XP plus something. All right, so let's call it Y for now. And let's plug in and see what problem Y satisfies. So A times XP plus Y is equal to B. Right, what's going to be true about Y? Well, let's distribute. So AXP plus AY is equal to B. But remember, we said that AXP has got to be equal to B. So these guys are the same. So AY is equal to the 0 vector. And the general solution of this is therefore going to be the general homogeneous solution of the system. Okay. So that's what's going on. This results really is telling you how solutions are always organized for a linear system. If it's a non-homogeneous linear system, you can always think about your set of solutions as a particular solution to the full non-homogeneous problem, plus the general solution or a general solution to the associated homogeneous problem. That's true in algebra. We'll see that there's a version of this that's true for differential equations. When we get to differential equations, the idea is really always lurking, at least in the background, if you're dealing with linear systems. Okay, so does this make sense to everyone? Are there any questions? Okay, so does everyone have what they need from this page? Is everyone okay? All right, so let's look at sets, linear combinations of vectors. I can't spell. Combinations. Okay. So when we look at the system, AX is equal to B. Okay. So let's just write out a particular example, small size, so it's not too horrible to keep track of everything. Okay. So I'm going to assume X and B are two component column vectors. A is a 2 by 2 square matrix coefficient. So if I multiply out, I have A11 times X1 plus A12 times X2, A21 times X1 plus A22 times X2. Okay. And I'm going to notice that I can think about this problem in a slightly different way. I can think of what I have here when I do that matrix times vector on my left-hand side. I can think of what I have in the following way. So when I multiply a matrix times a vector over here, you can think of what you're doing as taking linear combinations of the columns of the vector, right? Notice these vectors that I pulled out, A11, A21, that's really the first column of my matrix. A12, A22, that's the second column of my matrix. Okay, so it turns out that it's useful to think about the process of taking linear combinations of vectors in a little bit of detail. So, so that's the motivation for what we're doing. Does everyone have what they need from this page? Everybody good? Okay. So we can talk about the span of a set of vectors. Okay, this is a concept that's directly motivated by thinking about what's going on here. In order to solve this system, right, AX is equal to B, we're looking for the X. Effectively, what we're doing is we're making a linear combination of the columns of our matrix, and a solution is telling us what coefficients do we need, right? We're going to add together a linear combination of the columns of our matrix with the right coefficients to get the right-hand side vector. Okay, so when we talk about the span of a set of vectors, so S is a set of vectors. Right, so what is the span of S, or the span of that set? That's the set of all the linear combinations of the vectors. Right, so i.e. any vector right, if you can build your vector by taking a linear combination of those vectors in your original set, then it's in the span of the set. And there's a pretty direct geometrical meaning here. So for instance, think about this in three-dimensional space. If I give you a vector, and I'm going to write it as a column vector now, I don't know, 1, 2, 3. The span of that set of vectors is equal to for any real number x1, I take multiples of that basic vector. Well, 1, 2, 3. So here's my basic vector. I could take 0 times that vector. I just get the point at the origin. 1 times the vector gives me the vector. 2 times the vector gives me a point out here. And in general, what am I going to get? The set of all of these is going to be a line. Remember back from 243, where you might remember this notation for, that's the vector equation for a line. What are we really doing here? Well, our base point is the origin. We're taking all linear combinations of a certain vector, and that geometrically represents a line in three-dimensional space. If you take the span of two vectors which are not multiples of each other, they're non-zero vectors, not multiples of each other in three-dimensional space, the set of linear combinations of all of those two vectors is going to represent a plane in three-dimensional space, and so on. Okay, so that's an idea of the geometry that's going on in the background. Looks like we're out of time, so that's where we'll stop for today. So you should have enough to make a good start, at least on the third and fourth WebAssign homeworks. So please, if you haven't started yet, make sure you get the first two done today, and start taking a look at the third and fourth if you haven't done that so far. I can hang around for a little while if people need need to ask questions. Otherwise, you're free to go, and I hope you have a good day. And I'm getting close. The lecture notes should be updated soon.
And then I was just gonna ask once again, like with the schedule, if there's anything that should be coming up soon along with the syllabus. Just like if we have any upcoming exams or whatever, we can know when those are.
Yeah, the first exam's not for a little while, so don't worry about that for now. I'll get the syllabus up as soon as I can.
All right, thank you. Have a good weekend.
Thanks, you too.
Yeah, I just want to let you know